Hello, welcome everyone. Today we're very happy to have Nina Zubrilina, who will tell us about modular forms and their statistical properties. And how would you like people to ask questions?
Yeah, I should preface this by saying that it is very difficult to do justice to the entire field of modular forms within 1 hour. So please do ask questions, and I'm just hoping maybe if you get interested, you will then go and learn more about it on your own. Okay, so
Should they
yeah.
post them in chat or unmute, or what do you want them to do?
Oh, unmute is fine, or either. I just probably won't be able to monitor the chat too closely, but if you see questions.
Okay, sounds good.
Okay, so it is sort of customary to start the conversation about the theory of modular forms by this story about an observation of Ramanujan around, I think, 1916 or so, about a very peculiar looking function, if you see it for the first time, which is now called the Ramanujan tau function, and it is defined by the following series. So we define tau of n for n in the natural numbers the following way. So consider the identity, so tau of n times q to the n, where q is just some variable, is defined to be equal to q times the product, so n greater or equal to 1, q times the product of m greater or equal to 1 of 1 minus q to the m to the power 24. So what this means is that we take this side, we formally expand it into a power series, and you will get a bunch of q to the n with some coefficient. And you define this function tau of n by these coefficients. So just to give you an idea, tau of 1 is 1, tau of 2 is minus 24, tau of 3 is something like 252, and then they start growing pretty fast. So tau of 4 is like minus 147, 7, 2, and so on. So there are some natural numbers. And Ramanujan, just like being Ramanujan, magically noticed the following two things. The first one is that for m and coprime, so if they don't share any factors, tau of m times tau of n is equal to tau of mn. So it's multiplicative. And the second thing that he claimed is that for a prime number p, tau of p will always be at most 2 times p to the 11 over 2, which is, I don't know how you noticed that, but again, I think his formal justification was that it looked highly probable or something like that. Anyway, typical Ramanujan business. And so he just kind of observed it numerically and said that it's probably true, but he didn't really explain why it should be true. He just kind of claimed it. So the first of these two claims was almost immediately proved by Mordell, like a couple of months later. And the way that he proved it is that he recognized, so Ramanujan was not familiar with the theory of modular forms, but Mordell immediately recognized that this series defined by this product expansion is secretly encoding something called the modular form. And because that theory already sort of existed for 50, 60 years, it was known that something that is called the modular form, which I will talk about, satisfies this property. The second statement turns out to be much deeper. It's also a statement about modular forms that I will try to get to, but it took 70 more, 60 more years to actually prove this. So this is like a very deep theoretical statement. So what is a modular form? We're going to have to start by defining two objects. The first object is something that is usually denoted by the letter H, And what it is basically just the upper half plane. So we consider the set of complex numbers, see? And we consider the set of complex numbers for which the imaginary part is positive. So it's the set of x plus I times y, such that y is bigger than 0. So just think of it as, not the entire plane, but you just take the upper half. Okay? And the second object that we need to consider is something that is usually called SL2Z. So it is a group, meaning you can multiply its elements. And what it is the set of all integer matrices, so A, B, C, D, such that AD minus BC, which is called the determinant of the matrix, is equal to 1. And this is a very large group. There's plenty of such things. Okay, so we have the space and we have the group. So the way that we connect these two things is by something called Mobius transformations or linear fractional transformations, depending on the terminology you prefer, which is the following. So this group has an action. So it can act on the points in the space. And what I mean by that is that if we have an element A, B, C, D in this group SL2Z, and we have a point Z in H, then we can define, let's call this gamma, then we can define like an action of gamma on Z given by Z going to AZ plus B divided by CZ plus D. So that is called the Mobius transformation. And the reason that this is a proper action is that you can verify that the imaginary part of AZ plus B for any integers A, B, C, D times divided by CZ plus D will be equal to AD minus BC times the imaginary part of the number you started with divided by CZ plus D squared. And since we limited ourselves to having this determinant be equal to 1, if you started, you can see that, so this thing will be 1. This will be the same as the imaginary part of Z, and this is some absolute value squared. So what this means is that the absolute value of the imaginary part of this will also be positive. So if you take an element in SL2Z and you apply it in this way to some number Z, sorry, it's confusing, there are two different Z's. One of them is the integers and one is a point in the upper half plane. But if you perform this operation, then you will once again end up in something in the upper half plane. So, sorry? Yeah, and the reason we kind of formulate this in group terms is that, sorry, someone's saying something I can't hear very well.
I think it's just someone accidentally unmuted.
Oh, no worries. Okay. Yeah, so the reason I'm formulating this in group terms is that this operation combines well, basically. So if you take two matrices and you first apply one of them and then the other, then the result will be the same as first multiplying the matrices and then just applying the one matrix. So it kind of commutes on the two sides. Okay, so now we can define what a modular form is. So, definition. So a modular form it's called the form, but it's actually a function. So it's a function. So it's a function f that goes from the upper half plane to the complex numbers. That basically has a lot of symmetries under this transformations. So it's a function such that, okay, there'll be three properties, but the main one you should keep in mind is the first one. So when we input this transformation. So we take f of az plus b divided by cz plus d, which is the thing we were looking at before. Then this will be equal to cz plus d to some number k, which is fixed. K fixed. And it will just be an even integer times f of z. So if you know f of z and you give me a matrix and you apply the transformation, I can give you the value at the point which is the output of that transformation. Okay. Now you may ask, this is a very, like, the first time you see it, it should seem like a very strong condition because there are so many matrices in SL2Z. Why should such a function even exist? Why is there no inherent contradiction in having all these transformation laws? One thing I should mention is that the group SL2Z is generated by two matrices, 1, 1, 0, 1, and 0, 1, minus 1, 0. So what that means is that for any matrix in SL2Z, for any matrix of determinant 1, I can take just these two, and if I combine them, possibly I need to combine them a million times, but by continuing to multiply them with one another, I can produce anything that is in SL2Z. And what that means is that, oh yeah, sorry, I forgot. There's a second law that basically I'll just call regularity. Don't need to go into it, but think of it as being, you know, nice, continuous, doesn't go too crazy all over the place. So it's like a nice function. Yeah, so because this group is generated by these two elements, this first rule basically reduces to just two. So the first one is that f of z plus 1 will always have to be equal to f of z. And the second one is that f of minus 1 over z has to be equal to z to the k f of z. So as long as just these two things are satisfied, everything will be true here. So this implies this. Let's see. Okay. So, now let me show you a picture of one such function. Sorry. Okay, so what are we seeing here? This is the upper half plane. So this is, you know, this is the x-axis, and this is the y-axis. And each point in here is represented by two parameters. One is how bright it is, and that, so brightness is the absolute value of the complex number, so how far it is from the origin. And the color basically represents where it is on the, it represents the angle where it is. So if you take the upper half plane, say this is the origin, you take a complex number, there's an angle. So these functions look very funky. But so there's one thing I want you to notice in this picture, and that is that it looks sort of periodic, right? And that represents exactly the fact that when you move by 1, so the distance here is roughly 1, and we said that f of z plus 1 has to be equal to f of z. And this is exactly what you're seeing here. So when you shift by 1, you kind of come back to yourself. Sorry. Okay. One reason that this is important, so that there are just these two rules, is the notion of something called the fundamental domain. So fundamental. So let's look at the upper half plane again. We've already said that when you shift by 1 in this direction, the function comes back to itself. So if we want to understand what this function looks like, you know, we only need to understand it on one strip that is horizontal, because for the rest of it, it will be the same. So we can take the strip minus 1/2, 1/2, and everything else is kind of redundant information once we impose these rules. Well, it turns out that the second rule, this minus 1 over z, imposes a second redundancy, which is if we take a circle, that was not a good circle, of radius 1, basically what's going on above the circle determines everything that's going on inside of the circle. So there's something called the fundamental domain for SL2Z, which is this region intersect a strip between minus 1 and minus 1/2 and 1/2, and the circle between minus 1 and 1. And kind of as long as we know what the function is within this region, we know what it is everywhere. So this is called the fundamental domain for an action of a group on something. Okay, so now what are some examples, not visually, but can we write down some examples of this crazy looking function? Well, example number 1 is the function 0, because if you look at this rule, well, if the function is trivially 0 everywhere, then yeah, this is true. I don't know, just stare at it for a second to see it. Okay, another example is the function of Ramanujan. Which, again, unclear how he arrived to it, because to my understanding, he did not know what a modular form was at that point, but he found it. Just one more example, just to see it, is there's a function called the Eisenstein series, which is defined. So it's labeled by k, which was that parameter which we fix, and it is defined to be the sum over integers such that they're not both 0. Of 1 over m plus n z to the k. So as long as this k is equal to the other k, this will be an example of a modular form. I should say that this number k is usually called the weight of the form.
There's a question in the chat. Why is Ramanujan's function specifically to the 24th power?
Well, because, yeah, so the weight, good timing. So there is this parameter k, which is, for our purposes, an even integer. And in the case of the Ramanujan function, the weight of the Ramanujan function is 24, which is 2 times 12, which I will bring up again in a second why those two numbers are, one is a factor of another. But yeah, so it's a modular form of weight 12, which is the first weight for which there is a modular form for this group. So it's like the smallest weight example. Okay, so one reasonable question that you might ask after seeing this crazy definition is, why would you ever want to study such a crazy looking thing? And the answer is, again, it is very difficult to justify in an hour-long lecture, but there is kind of a very famous cliche quote of a German mathematician whose name is Eichler, that there are 5 fundamental operations in mathematics, and that is addition, multiplication, subtraction, division, and modular forms. So it's kind of this crazy looking thing that you somehow encounter in all sorts of different areas of math over and over. And even though it seems unintuitive, it just comes up somehow, one way or another, everywhere, at least in number theory. Yeah, so one kind of maybe slightly more intuitive way in which you can define a modular form is through an operation on the space of lattices instead of the upper half plane. So let me just remind you. So a lattice. So a lattice is basically, in two-dimensional space, is what do? You take two vectors, for example, 0, 1, and 1, 0. And you take all of their linear combinations. So for these particular vectors, you would get a kind of grid. I'm not going to be able to draw the entire grid, but it's an infinite grid that goes in all directions, where you take these 2 points or 2 vectors and you just combine them in all possible ways. So this would be something called z2, z squared. Okay. Yeah, so just think of it as being like an infinite grid that is highly symmetrical, where you can add points. It doesn't have to be orthogonal. You can take this point and, I don't know, this point, and okay, you can just imagine what happens when you add them all. You get something slightly more regular, but very regular. And so I'll denote lattices by the letter lambda. One slightly different way you can think about a modular form is that it's a function on the space of lattices. So it's a function f that goes from all lattices in, let's say, in R2 or to C. And the reason that it's the same thing is the following. So, oh yeah, sorry. It's a function that satisfies the fact that, second, such that, again, it satisfies a transformation law. So if we take an alpha, any complex number, and we scale the lattice by this number alpha, meaning, if alpha is 2, you just make it twice as large, but if alpha is complex, there's also some rotation element. So, but you literally take every point and you like multiply it by some number alpha, which is like, I guess you could visualize as going potentially out and rotating. So for any alpha, the function at alpha times lambda is equal to alpha to the minus k f of lambda. So once again, we have some kind of space of things that we can add and multiply, and we're imposing a scaling rule on what happens when we transform the lattice in some way. And the reason this is the same thing is because, so you can think of lattice lambda, any lattice lambda, as being some vector v1 times z plus some vector v2 times z, right? Because we said we take 2 points and we look at all of their linear combinations, and we can always find an alpha such that if we rotated the 2 vectors correctly, then one of them would become equal to 1. So for example, take alpha where you just divide by v1, and the other one would become something in the upper half plane. And because of that, as long as you know what this function does on the upper half plane, you know what it does on all the lattices. And if you kind of stare at it for a bit, you will see that the scaling operation is exactly secretly the same as what we said about the function before. Yeah, I don't know. I find this slightly more intuitive. Yeah, so maybe this should be an exercise. It's not extremely difficult. What I've explained so far is only why the spaces are kind of equivalent, but the scaling, you can see there's also an alpha to the minus k, and there was in here there was also some scaling by a power of k. Yeah, okay, but the real reason that, like I said, that these are good objects to study and to look at is that you can prove a lot of really cool stuff using them, using the theory of modular forms about seemingly very unrelated things. So for one, you can prove something like this Ramanujan thing. And for example, if you've heard of Fermat's last theorem, the last key ingredient in the proof of demonstrating that it is true had to do with demonstrating something very fundamental about the theory of modular forms. Okay. Now, so one more thing I want to mention about modular forms is that, once again, just looking at the definition, you can immediately see the following. So if F and G are modular forms of the same weight, and again, let's say alpha is some number, I don't know, number. Then you immediately get the following two things. The first is that F plus G is also a modular form. And alpha times F is also a modular form. And what this formally implies is that the space of all modular forms of the same weight, so space of weight A forms for fixed K is a vector space. Which, again, you'll probably know what that is, but well, all it means is that you can add and multiply elements, and it's sort of like, yeah, it's a space where you can operate on things. And it turns out that it's always finite dimensional. So again, a priori, it's not clear why modular forms should even exist, just from the definition, but it turns out they do, but there's not that many of them. There's always, for a fixed K, there's always a finite space of modular forms. And moreover, there's a very special basis that will become relevant slightly later. Special basis. There's kind of a distinguished basis in the space, so there's a distinguished kind of choice of set of directions that generated, which is called the Hecke basis. Okay. Now, so if you remember, we started with two facts. One was this multiplicativity, which again was already known at the time when Ramanujan discovered this. And the second one was this kind of tricky, strange seeming inequality where there was, I should preface this by saying, since there was a question about 24, that this 11 is related to this 24 by being 24 divided by 2 minus 1. So nothing is a coincidence here. Yeah, and so the reason that second inequality is related to the theory of modular forms is that, so modular forms will always have a different presentation, which is called the Fourier expansion. It will look something like the sum of n greater or equal to 1, a of n q to the n, which you can see looks very similar to the power series expansion that Ramanujan had. And here, in case you're curious, the variable q is related to z by being e to the 2 pi I z. So you can always, in terms of this variable q, you can always rewrite the modular form with this kind of expansion. And it turns out that for any modular form of weight k, it's always true that a of n in absolute value is less or equal to the number of divisors of n times n to the k minus 1 over 2. So this k minus 1 over 2 is, yeah, exactly what we saw, this 11 n to the 11 over 2, and d, you know, for primes, this divisor function is equal to 1 because p is divisible by 1 in itself. Yeah, and this result was a consequence of like a very deep theorem by Deligne. It is called the Weil conjectures. It is a consequence of the Weil conjecture, one of the Weil conjectures. And it is a much more modern development in this theory. So this statement of Ramanujan was not known until, like, formally known until the 70s or something. Yeah. So
Is there a formula for these an, like explicitly, or we only know the bound?
explicitly, well, it depends. There are many modular forms, right? So we
Okay.
don't know. They will be different for every single form. For the tau function, there's no explicit function. There's no other form in which you can write it, as far as I know.
And is like the basis finite or infinite? It's infinite, right?
No, it's the basis is finite. So the dimension of the vector space is finite, and so because of that, it will always be finite dimensional. So you can always just pick, I don't know, whatever the dimension of the space is, many forms. And again, there's a very special choice of basis that satisfies very nice properties. Oh, I should say, yeah, this is true for. This is true only for these special basis elements. So, and it so happens, well, in the case of weight 12, it's a one-dimensional space. So this tau function is automatically this basis element. Yeah. Right, okay. So now I want to slowly get to the statistical part. So, statistical. Okay, so what do I mean by statistical properties? We have this wonderful bound of Deligne, which tells us in particular, so if we take p prime, just like in the case of the tau function, a of p will always be at most 2p to the k minus 1 over 2. And I should also mention it will always be real, even though a priori we don't know that, but it could be Fourier theory doesn't immediately tell you that the coefficients of a Fourier expansion have to be real. But in this case, it turns out that these coefficients will always be real. For the tau function, you saw they were integers. Right, and what that means is that we can always take our coefficient AP and we can scale it down by this size p to the k minus 1 over 2. So fix a form. So fix f. Take this coefficient, and that is now always a number that simply lies in the interval -2, 2. So now we have, so for all primes, so for f fixed and any prime p, we get some number. And then the natural question is, well, what starts happening when we start to vary this p? Is there anything we can say beyond the fact that it's always between -2 and 2? And as it turns out, so because it's a trapped parameter, it's an interesting question. Always in like arithmetic statistics and number theory, people love asking these sorts of questions. And it turns out that the answer is yes. And this is, again, a very modern very deep result. So there's a conjecture of Sato and Tate. Which is now a theorem by like 7 authors. I'm not going to write down, but no theorem, which states the following. So as p goes to infinity, basically, as we take more and more p's, we converge. These coefficients will always converge to a very concrete distribution. So there is convergence. And you can visualize this convergence in the following way. So take this interval minus 2, 2, where we're trapped. Draw a I'm not very good at aiming with semicircles, but take a semicircle distribution. So 2 over pi square root 1 minus t squared. The 2 over pi is there to make the total area equal to 1. And if you want to ask, take two numbers, say alpha and beta. And if you want to ask how often will the coefficient, the scaled out coefficient, lie between alpha and beta, you compute this area. This will be some number less than 1, and that will be the probability. So we know exactly, as we take more and more primes, what proportion of them will fall between any two numbers. And this is called the Sato-Tate distribution. So not only do we know this bound on the sizes, but we know exactly kind of what, that is not a statement about any particular prime. Maybe until 10,000, the convergence is terribly slow and things can be all over the place. But eventually, if we go far enough to infinity, this simply has to happen. Okay. So now I will try to briefly talk a little bit about how this is related to my thesis. But before I get to that, I should mention the connection of this entire story to elliptic curves. So what is an elliptic curve? In some sense, you could say that an elliptic curve is the first non-trivial example of an algebraic curve. By algebraic curve, I just mean take x and y, write an equation in x and y. That is something. That is something that you can draw. That is something that you can study. And people will often want to understand the set of points that these curves have over various domains. So for example, over rational numbers, over complex numbers, over the integers, over finite fields, etc. Why is it the first non-trivial example? Well, okay, the simplest curve is a line, right? Take a line, I don't know, x equals y. If you want to understand the set of all rational points on a line, that is very easy to do. The set of rational points on a line is a over b, where a and b are in n, right? So we can completely parameterize the entire set of points on this line. Similarly, if you take a degree 2 equation, so for example, x squared plus y squared is equal to 1, take a circle. It's maybe slightly less obvious, but we can parameterize the entire set of rational points on the circle. Well, integer points you can probably parameterize in 2 seconds. Rational points are called, they're parameterized by Pythagorean triples. And again, there's a parametric equation that you can write down to literally list them all. But it turns out that the second you go to degree 3, so the usual form in which you write an equation for an elliptic curve is y squared is equal to x cubed plus some number a x plus b, this becomes immensely difficult. So this curve on the plane will look something like this. So it's still a curve, you can still draw it, but it turns out that finding the points on just 1 degree higher curve, it's sort of an art. There used to be papers dedicated to just taking one example of such a curve and like proving that it has a certain set of points. Okay, so for example, this could be x cubed plus x plus 1. But what we do know theoretically is that the set of points, even though we don't know what it is, it can always be, it always has to have a certain form. So it turns out that there's secretly a group law on this curve, kind of like there always is on a line as well. You can take 2 points, you can add them, you'll still get a rational point. Turns out it's a slightly more sophisticated law, but there's always a group law on the set of rational points of an elliptic curve. And we know that it's always an abelian group, and it has some finite part, which I'll call torsion. So for example, think z mod 2 or something. And it has some infinite part, which is z to the r. So there's some number r in the natural numbers, sorry, in the non-negative numbers, such that, yeah, it just has to look like this. And if you haven't thought about groups very much, just think of it being, so we know that it's either a finite set of a very particular form, or it's infinite, and then this number r, which is called the rank, kind of encodes how infinite it is. So if it's r is equal to 0, then there's just finitely many points. If r is equal to 1, there's basically integer many points, and so on. Okay, so this was a very quick introduction to the theory of elliptic curves. And so one extremely interesting thing about elliptic curves is that, so we've been talking about looking at rational points, right? But you could also look at finite points, finite field points. So for example, take the curve y squared is equal to x cubed plus x plus 1, and take, I don't know, z mod 13 or something. So there are finitely many pairs of x and y that you can plug in, right? There's 13 x's and 13 y's. And by plugging in all of them, you can find the exact number of solutions to this equation in z mod 13. And it turns out, okay, so from that you can produce a coefficient, which I'll again, for a good reason, call AFP. So just think of it as, it's not exactly the point count, but just think of it as being the number of solutions over, like in modular arithmetic. Well, it turns out, and that is Fermat's last theorem, that not quite using SL2Z, but if you slightly modify the group, so if you change SL2Z to, again, a group of matrices, but A, B, C, D, such that C is congruent to 0 mod some number n. So if you consider a larger set of different groups and you do the same thing, you define a modular form in the same way, then there always will exist a form yes, that's gamma naught of n, of weight 2, such that basically its coefficients that we've been talking about is the same as elliptic curve AP. So this is a very profound, very difficult to prove, and to me, kind of still an unexpected looking statement, which is that if you want to count points of these like mysterious curves over finite fields, you can always find a modular form, which is unclear how it's related a priori to something like an elliptic curve, and you can take its coefficients, and its coefficients will be the same as counting points on some curve. Amazing stuff. Okay, I will try to finish by just very briefly explaining what my thesis is about. So my thesis started with a number of computer scientists who were basically trying to do machine learning on ranks of elliptic curves. So they were trying to take these APs, so take an elliptic curve, take a bunch of APs, and try to predict the rank. Guessing the rank is very important. So being able to predict this number R of an elliptic curve, again, it's not very easy. You can't just look at it and immediately see it. You have to do some work to be able to do it even conjecturally. And so they were taking AP for, say, P going up to, I don't know, 10 to the 10 or something. But you can't really do that much, but let's say 10 to the 5 or something. So compute a whole bunch of them, which again, unlike predicting the rank, this is very easy to do because you just have to go through a finite number of pairs of things for each individual P. And they were trying to get the computer to guess R. Okay. And they noticed that somehow they were able to do it extremely well. So their prediction power was very, very high. And by trying to kind of analyze what their model was doing, they noticed the following thing. So picture number 2. Okay, so they noticed that depending on whether the rank is even or odd, there's a strange oscillation in the AP in these AP coefficients. So what this picture is one of the colors corresponds to rank 1, one of the colors corresponds to rank 0. So that's that number R that I mentioned. And this is a plot where on the x-axis, so the x-axis has P basically. So this is the p-axis. And the y-axis is the kind of the AP-axis. But this is not for one individual elliptic curve. This is kind of on average. So they would take a whole group of elliptic curves and compute the average of AP for a fixed P. So Y has average for a bunch of P. For a bunch of E, sorry. So let me just repeat. Take a whole bunch of primes going up to 10. In this case, I guess something like 8,000. And take a whole bunch of elliptic curves ordered in a certain way. No, it doesn't. It only happens on average. So they have to be ordered in a particular way. You know, I didn't tell you how you're grouping the elliptic curves, but that's not important right now. And compute the average of, on the y-axis, the average of these APs and plot it as a function of P. And they saw that for rank 1, it does this, and for rank 0, it does this. And the reason we're looking at rank 1 and rank 0, by the way, is that kind of most of elliptic curves it is still conjectural, but are predicted to have rank either 1 or rank 0. So this shouldn't be too different from looking at all curves. Yeah, so they saw this, and they were naturally mystified by what's going on. Yeah, and then they went out and asked my advisor if he knows what it is, and he was like, this should be your thesis problem. And that was basically my thesis problem. But it wasn't quite, because we still can't really explain, or prove at least, why this happens for elliptic curves. But as I have told you previously, there's this very profound statement that we can understand the set of APs for elliptic curves as kind of a thin subset of the set of APs for all modular curves, all modular forms. And basically my theorem, I won't write it out fully, was an analogous statement for coefficients of modular forms. Of the special basis of modular forms. Yeah, okay, I think I'll finish a bit early because a lot of things to say.
Okay, thanks for a great talk. So are there any questions?
Was there anything in the chat that I missed? No.
Okay, so if there are no questions, then thanks, and move on to the next part of class now.
Okay.
Bye for now.
Thank you for the invitation. Oh, there's a mess. Oh no, never mind. All right, bye-bye.